Good afternoon, everybody. So welcome to this MOX colloquium. It's a great pleasure to have today talk by Prof. Stevenson. Professor Stevenson is Professor of Applied Analysis at the University of Amsterdam, the Netherlands. He received his PhD from the University of Utrecht in 1990, years ago. A few years ago. And before obtaining and being appointed professor at the University of Amsterdam in 2007, he worked in the University of Utrecht, the Eindhoven University of Technology, and the Rabat University. And he served, actually serving in the editorial board of several prestigious journals in numerical analysis and computational mathematics. He's a leading expert in numerical methods for approximation of partial differential equations, and the main focus of his research is on finite elements, on wavelet method, multi-element solvers, least square discretisations, adaptive methods, and space-time methods. Let me mention that Rob obtained several important results, breakthrough results. Let me mention just one of them. Both in the wavelet context and in the context of finite elements, he obtained a very deep result that opened the door to prove the optimality of adaptive wavelet methods and adaptive finite elements. So today is a great pleasure to have him here, and he's going to talk about time-space finite elements methods for parabolic flows. So please, Prof, the floor is yours.
Thank you very much for the kind introduction and for being a perfect host here. So thank the organizers for having me here. You mentioned already the title? No. So the title is Time-Space Finite Element Methods for Parabolic Problems, and this is in parts joined with Lars Diening and Johannes Storm for one part, and another part I did it with Gregor Dampner. So this is the outline. I will first give an introduction, explaining the difference between time marching methods and monolithic solvers. Monolithic solvers where you solve the problem as one big problem and not as a sequence of problems. And I will present three different monolithic solvers. All have their pros and cons. I start with the classical time-space variation formulation, and then the parabolic problem defines an operator from some domain to a codomain, and we are going to minimize the residual in a codomain. So we take a finite dimension subspace, put it in the equation, and minimize the residual in the codomain. But the codomain is a dual space. So that's a bit complicated because you cannot exactly evaluate dual norms. So we are going to reformulate it as a saddle point problem. And if you have saddle point problems, you need to satisfy an insert or LBB stability condition. Colloquia is nearby, so I guess most of you know the LBB condition. And we are able to satisfy this condition if we use prismatic finite elements in the time-space cylinder. So prismatic elements, I take simplicities in the spatial domain and I tensorize it with intervals in time, and then you get these prisms. And the case for which we can prove the stability is the time slab setting, it's depicted here, and I take here for simplicity, I cannot draw very well a one-dimensional domain. And a time slab setting means that I can subdivide my mesh into time slabs. For each interval in time, you have the same mesh. And for this type of meshes, we can prove the stability. But we are not completely satisfied with this setting, because suppose I have a corner singularity, then I want to take very small meshes near the corner. But if I refine the mesh in time, then in the time slab setting, if I refine somewhere in time, I have to do this refinement uniformly in space. So you cannot do refinements near a corner or so. Okay, and I'm interested in adaptive refinement techniques and optimal meshes, and for that reason I don't like this restriction. So the second method, number 3, that we are going to discuss is a variational formulation that involves fractional norms. And in that setting, this is joint work with Lars and Johannes, and in that setting, we can we use again prismatic partition, but now we can do local refinements simultaneously in time and space. So in this illustration, we refine towards the corner because there's a singularity apparently. You get hanging nodes. It's not so nice for implementation, by the way. It's a bit complicated. But there is a restriction. Now we need parabolically scaled prisms, meaning that the diameter in time of a prism should be proportional to the square of the diameter in space. That's what you see. You get here very thin prisms. Okay, and then if time permits, I hope it does. The third formulation I will present is a reformulation of a parabolic equation as a first order system. And then the codomain, so the operator maps, the space in which the operator maps is L2, or multiple copies of L2. And we can compute L2 norms, so we can do minimal residual methods without forming saddle point problems and so on, because we can compute L2 norms. So that's very easy. We don't need any LBB, no, don't have a saddle point. And for this problem, I will show you some numerical results and give some applications. But also this formulation has some disadvantages, as you will see. Okay, but I should, of course, emphasize the advantages. Some background about numerical solution parabolic PEs. So what you normally do, think of the heat equation. You discretize in time first, and then what you have to solve is a sequence of elliptic problems. And so you say Euler backward in time, and then in each time step you have an elliptic problem, and you discretize and say with finite element methods. So that's what people normally do if they solve parabolic problems. And I must say, if your problem is smooth, the solution is smooth, there's nothing against this. You have you assume some smoothness of the solution, you have error estimates and so on, but it becomes more complicated when you have a solution which has singularities, so which are non-smooth, and then it might be useful to think of other approaches, the monolithic approaches. So with the monolithic approach, you are not going to solve your parabolic problem as a sequence of elliptic problems, but you solve it at once. So what is the disadvantage then is that you have to solve a d+1 dimensional problem instead of a sequence of d-dimensional problems. Yeah, so you need more memory for doing that. Often you are not solving just a parabolic problem, but maybe you do it in the framework of an optimal control problem, and then your forward problem is coupled with a backward problem, so that the advantage of time marching that you at each step you only have to solve a simple elliptic problem vanishes then, because everything will be coupled. Okay, so for optimal control problems, this is not a real disadvantage of the monolithic approach. There are also some pros. With the monolithic approach, you get a much better parallel complexity, and although I don't work in that, I think this is the main motivation for people to consider this approach. And you have an additional time dimension that you can use for parallelization. I know also that traditional time marching schemes can be parallelized to some extent with the parallel method from Monday and others, but the parallel complexity of this method is much better. And what I think is very important for me is that we can guarantee that we get a quasi-best approximation from the space we employ, like Seyer's lemma for elliptic problems. So from the finite element space that we employ, we get a solution in that space, and we can show that it is up to a constant factor the best approximation from that space. And that is a necessary condition in order to get optimal adaptivity. And so from each space that you generate, you should be ensured that from that space you get up to a constant factor the best approximation. Otherwise, you can never get optimal adaptivity simultaneously in time and space. And we observed it, but we cannot prove it yet. we use least squares methods. And for least squares methods, you have an obvious estimator which breaks into contributions from elements. So it is perfect for doing additivity, but to prove that you get the optimal mesh, that is harder. Maybe you know more, but there are some developments in that direction. But we don't have that yet. And I will also show some application with the reduced basic method. If you do reduced basic method with time marching methods, you only reduce the complexity in space, but not in time. And with this method, you also reduce the complexity in time. The first people that worked with the monolithic approach were Bushka and Janik in the late 1980s. But at that time, there was not so much interest in those methods. But from 2010 onwards, approximately, there is more interest in those methods. And as I said, I will discuss 3 monolithic methods. Okay, this is the first. Consider a parabolic problem like this. Initial problem, this is a parabolic equation. And I have a Galvin triple. Maybe let's immediately go to the example. The leading example is that H is L2, the space K is H10, and the operator AT does not depend on time in that setting, and A is just the variational formulation of minus the Laplace operator, and then you see here the heat equation. Yeah, so think of the heat equation. Okay, and now we have to form a variation formulation. So what we do, we multiply the parabolic problem with the function phi, and we integrate over the time domain, and that's our variational formulation parabolic problem. Actually, this is also involves an integration over space, because this A, as you see, is already a variational formulation of the operating space. So this is actually an integration over the time space. Yeah? So this is our variational formulation. And in order to close the equation, we have to impose an initial condition, and that's done by the trace operator. So gamma 0 of u is just the value of u in 0, and it should be equal to the initial data. So the complete operator is B. It's a pair of B1 and gamma 0, and it should be equal to the given data. And before you go to the merge, you would like to know that your equation is well posed. And that's true. We have to select, of course, suitable spaces for the solution and for the test functions. So the solution will live in the space L2 in time. This is time interval, taking values in K, say H10, intersected with functions which are H1 in time, taking the values in K prime, which is H-1 in this example. And the test functions live just in L2 in time, taking values in H10. And with those choices of spaces, you can prove, has been proven, that this operator B is boundedly invertible. This is my notation for a linear isomorphism. So it's a linear operator, this isomorphism from U to phi prime times H prime. And H is, say, L2, and so H prime is you identify with L2. But this is a real dual space. Okay, so we have well posedness, but we have a problem because the codomain of the operator is not the adjoint, the dual, I should say, the dual of the domain. So you cannot simply do Colloquian discretisations. Yeah? So you have to do something else. You can think of Petrov-Colloquian, but we do something else. Petrov-Colloquian is not easy to do. So we use the least squares discretization. So we simply minimize the residual of the equation in this norm. And that's what we do. And that sounds simple, but here you have a dual norm. This H prime is harmless because it's just identified with H. But here we have a real dual norm. So how you can evaluate it? So it looks simple, but it is not that simple. Okay, let's to understand how we can solve that. I go to an abstract setting. So I have an operator. It's boundedly invertible from a space U to the dual of Y. this is the equation we want to solve, a well-posed equation. I have a family of, say, trial spaces. The delta, everybody notices with a subscript h, mesh size. I don't like this so much, but for me, I use a delta. Delta refers to discrete, but it's the same thing, right? So I have a family of discretization spaces, and then U delta is the minimizer of the residual. And this would be the best approximation to U from the trial space with respect to this, say, energy norm. This is quite obvious because the energy norm is just, if you're minimizing this energy norm, it's the same thing as minimizing the residual, by definition of this norm. But the good thing is that this norm is equivalent to the norm you're interested in. Because B is an isomorphism, boundary invertible, so this energy norm is equivalent to the norm you're interested in. So if you do this, you get up to a constant factor, a best approximation from the space you employ. That's good. The only thing is that you cannot do it because you have the y prime norm here, you have the dual norm. You cannot evaluate it. So what to do with that? So let's focus on the case we are interested in. We have an operator that has two components, B1, and this was kernel 0, you remember. But this is the abstract setting. So this y is a product of two spaces, and also the right-hand side has two components. I assume that h is can be identified with h prime, so the h prime norm is not an issue. So this is evaluable, but this guy is not. So what you then do, you choose a test space, also discrete space, it depends on your trial space, which is sufficiently large that this discretized dual norm, here you have a discretized dual norm, is proportional to the real dual norm when you apply it to B1W, where W is a trial function. You cannot expect that they are always equivalent because this is discretized norm, but W runs over the trial space. So the test space should be sufficiently large so that these are equivalent, meaning that the gamma delta, the intercept constant, is positive. And of course, we want to have this uniformly in delta. That's the LBB stability. Okay, then we do the following. We now do the residual minimization, but now instead of the real dual norm, we use this discretized dual norm. And here there's no problem. And if you do that, then you can prove, it's not so difficult, that what you get is up to a constant factor as good as the best approximation. So you are safe. If you take this discretized dual norm, assuming that you have this substability. Okay, now this doesn't look like an implementable method because this is a finite dimensional space, but you have to supermise over finite dimensional space. How you do this? Now you can do this. What we will do, we use the Rees lift of the residual. We introduce it as an additional variable. So this lambda delta is the Rees lift of this residual. And so if you take this into account a bit, then you can prove, it's not so difficult, that the U delta that minimizes this residual is the same as the second component of the pair that solves this saddle point problem. It's the same thing. It's just an implementation of this minimization process. Okay, and now you see also that this intercept condition is really an LBB stability condition that you know from saddle point problems, right? The test space should be sufficiently large compared to the trial space, and then you get stability when you solve saddle point problems. So it's the same thing. And the lambda delta from here is the Rees lift of the first residual. So it's like the second residual, but now the F1 minus B1 U delta in the discrete dual norm is equal to this lambda delta. So this is an error estimator. It's equivalent to the error. So this is a posteriori error estimator that we can compute, and we can use it to drive an adaptive routine. So on places where this is large, you refine and you continue. That's the idea. Okay, and sometimes in method 2 that I'll present later, we are very unlucky because not only the dual norm can, in that case, not only the dual norm cannot be evaluated, but also the corresponding primal norm cannot be evaluated. Maybe you remember in method 2 there were fractional norms, and the dual of a fractional norm is also a fractional norm. You cannot evaluate, but also the fractional norm itself cannot be evaluated. So then you are still in trouble because this inner product is part of the system, so you cannot evaluate, then you are dead, so to speak. So what you in that case do, you replace this inner product by an inner product defined by a preconditioner. So basically what you need, think of the stiffness matrix corresponding to the inner product. Suppose I have a preconditioner for the stiffness matrix. I call the preconditioner K. Then the K inverse is proportional to the stiffness matrix in a way, yeah. So we replace the stiffness matrix by a precondition or an inverse of a preconditioner, and then you get something which can be evaluated. Now, to be more precise, the inverse of this guy can be evaluated. And if you eliminate, you go to the Schur complement, then you get here the K itself. This is the preconditioner you can evaluate. Yeah? So you replace this by a preconditioner, an inner product defined by a preconditioner. Then you do the Schur complement, and you recognize maybe here the normal equations that you get with these squares approximations. You get the normal equations. That's it. So you can. The point is, even if you cannot evaluate the inner product, you replace it by something which is uniformly equivalent, and then you can compute it. And of course, you lose a little bit, but if you have an optimal preconditioner, these constants are bounded from above and below uniformly in delta, and you're still satisfied. Okay, so even with fractional norms, you can do this. What's next? Now I have to discuss situations in which we can realize the if subcondition. And as I said, we can do it for a time slab setting. It's described more precisely here, but not completely for general meshes. But let me describe the time slab setting. I take for you, this is a bit technical slide, but I take for you delta functions which are continuous in time, and on each time interval there are a polynomial in time times a finite element space in space. Yeah, so you take continuous in time, on each time interval it's a tensor product of a polynomial in time and a finite element space in space. And the test space is the same, except that you relax the continuity between time slabs. So it only has to be L2 in time, so it can be discontinuous in time. But then for the rest, it's the same definition. So the test space is a little bit bigger than the trial space if you have more than one time interval. Now, for this setting, we can prove LBB stability uniformly in all those finite element spaces. Okay, now the important question I would like to solve is, can we also have uniform if substability for families of finite element partitions of the time-space cylinder that allow for local refinements simultaneously in time and space? Now, on the next few slides, they are a bit directed towards the experts. I want to explain why we cannot do it. Yeah, okay, and then later I go to method 2, and then this finishes the first part. Okay, so what is the trouble if we want to do general meshes? I first want to recall the relation between LBB stability and Fortin interpolators. So I go to an abstract setting, I have an operator from U to V prime, I have a trial space, I have a test space, I want to have stability, I want that this gamma, this infimum of the discretized dual norm and the exact dual norm, where W runs over the trial spaces, I want this gamma to be positive. Yeah? And now suppose I have a mapping pi delta from V to V delta that satisfies this relation. This is the Fortin relation. So this is called the Fortin projector. Suppose I have a bounded projector then this gamma delta can be bounded by 1 over the norm of this projector. And conversely, if you know that gamma delta is positive, then such a projector does exist. Yeah. So in summary, having LBB stability is the same as having uniformly bounded Fortin projectors. So let's see whether in which situation we can construct such projectors. Okay, I go to a very simple situation. This is a bit technical, but it doesn't take long. So if you're not familiar with this, don't worry. So I go to the Poisson equation in 2D. So this is my operator A. It's just a variation formulation of the minus Laplacian. And I consider as trial space the continuous piecewise linears with respect to some mesh. May have local refined regions, and so it doesn't have to be crazy uniform, but it should have minimal angle condition. That's it. Now I do a strange thing. We know how to solve Poisson equation, just do Colloquia, it's easy, but we do the strange thing. I now want to minimize the residual in H minus 1 norm. So I do a least squares method, but I have a dual norm in which I want to do my minimization. So I make things complicated. Let's see whether we can do it. Now we cannot evaluate this norm, so we do the same thing. We replace the dual norm by a discretized dual norm. So take the dual of a test space. And in order to be able to do that, we have to construct a test space in such a way that there is a uniformly bounded Fortin projector. Because insubstability is the same as existence of a uniformly bounded Fortin projector. Now this is the Fortin property. Just the same thing as I displayed on the previous slide in an abstract setting. Okay, so this has to be 0 for all phi in H10 and for all trial functions. Now, if you write this as a sum of integrals over the triangles, and you do integration by parts, and you use the fact that the Laplacian of a piecewise linear is 0, then you end up with this condition. So what you should have a projector of phi to the test space such that identity minus this projector applied to any H10 function integrated over an edge in the triangulation should be 0. That should be 0 for all interior edges. So how do you make such a Fortin interpolator? You first start with constructing a projector onto your finite element space, which is locally bounded and also has locally an approximation property. The identity minus the projector is a factor h less than the H1 norm, the local H1 norm. This is known to be satisfied for, say, the Scott-Sang interpolator. Okay, this projector has some nice properties, it's bounded, but it doesn't have this property, so you correct it. So we add quadratic bubbles to our finite element space, quadratic bubbles, and we correct the Scott-Sang projector with a linear combination of quadratic bubbles. And then we satisfy this condition, and we also satisfy local boundedness. And if you sum over the triangles, you find at the end of the day that this guy is really a valid Fortin interpolator. Okay, that's a bit technical construction, but what are the essential ingredients? Now, the essential ingredient is that we have a Scott-Sang-like projector. A projector from the whole space to the test space, which has an approximation property locally, and which has an inverse inequality. And they should be complementary, so what you gain here, you lose there. Here you gain HK, and here you lose 1 over HK. And then you can combine things together, and then you can construct, adding some bubbles, you can do your thing. Okay, if we try to do this for the parabolic, here we have the spaces L2 and H1 that play an important role. If you go to the parabolic, the L2 will be the L2 space over the time-space cylinder. So this is a time interval, this is a spatial domain. And the H10, the role will now be played by our space phi, and that was L2 in time taking values in H10. Okay, and what's the problem? The construction of the Scott-Sang fails because this embedding, this was a compact embedding, H1 to L2, but this, if you go here, the embedding of this space into L2 is not compact. And then you can never have this approximation property, because only compact operators can be approximated by operators that have finite rank. And so this cannot hold for our pair of spaces. So I must say this insight came to us only later, so we first tried hard and so on. But you can actually quite easily realize that it is just not possible. Yeah? Okay, so then we became a bit pessimistic that we could prove this insubstitutability for general meshes. And so we went to method 2. I go a bit faster in method 2. I have to. So this was our operator. B was boundedly invertible from U to V prime times H prime. Yeah? If I now substitute U0 is 0, so I assume 0 initial condition, then there is no reason to test the initial condition. So I can drop the gamma 0 and just incorporate the fact that the function is 0 at 0 in the space. And so if I take B1 and I replace H1 by H1 0, comma, what does it mean? These are the H1 functions that vanish at t is 0. Yeah, so I incorporate the 0 initial condition in space, and I don't have to test with gamma 0. So B1 is bounded between those spaces. And if you do integration by parts over time, you realize that B1 is also bounded from L2 here to this space. So basically, I have interchanged the roles of test and trial spaces with one small difference. These functions vanish at t is 0, and these functions vanish at t is capital T. Now, small change, but if you have that B1 is boundedly invertible between two pairs of spaces, it is also boundedly invertible between the pairs of intermediate spaces. And that's here. If you have seen it, recognize it. If you have not seen it, it's a mystery. But here are the intermediate spaces. And you can characterize the intermediate spaces. They are isomorphic to spaces there. Okay, if you now substitute S as a half, then you get the following result. B1 is boundedly invertible from the space L2 in time, taking values in H1 0, H a half in time, taking values in L2, and functions they should vanish at t is 0. And the dual of Vf, F refers to fractional. There are fractional suburb spaces involved. Vf is L2 in time, H1 0, H a half in time, but now vanishing at the endpoint, taking values in L2. Yeah, so both UF and VF do not contain dual norms anymore, but they contain fractional norms. And there's always a price to be paid. And this formulation is nearly symmetric because the trial space is nearly the same as the dual space. So some people have employed this to cook up, to modify the method that operate a little bit by composing it with a Hilbert transform. And then you get something which is coercive, but the Hilbert transform is not local, so it has also some problems. So this is not what we do. What we would like to benefit from is that this new test space is compactly embedded in L2. So now we can have some hope that we can construct these local projections and that we can prove LBB stability for general meshes. And indeed, this is possible. Okay, I don't like that we have assumed that we have a zero initial condition. And on this slide, it is shown how you can include non-zero initial conditions. So you can, again, reintroduce the initial trace operator, and now you have to modify the spaces, and you still have that the operator is boundedly invertible, but we have different spaces. Yeah, I don't want to go into this also in view of the time. Okay, so what can we now prove? I will not comment on the proof, but now we can prove LBB stability in this setting. Let me go, maybe it's good if I just simply recall the first slide, second one. We can now show LBB stability for partition into prisms. You can do local refinement, you can allow hanging nodes, but the prisms should be parabolically scaled. Yeah, that was the contents of the slide. I just showed you. Where is it? Here. Okay. And the key is that with this new test space, if you have a function in the test space and you measure the approximation error in L2, you gain the diameter in space, the maximum of the diameter in space, because you have one order of smoothness in space, plus the diameter in time to the power half, because you have half of the smoothness in time, right? If you do an inverse inequality, so you have a finite elements function, and you want to estimate the norm in VF by L2 norm, you lose something, and what do you lose? You lose the diameter in space to the power -1, and you lose the diameter in time to the power -1/2. And what you need is that what you gain here should be the reciprocal of what you lose there. So you need approximation properties and inverse properties that are balanced in the sense that one is 1 over the constant that you gain here is 1 over the constant that you lose there. And that's the reason why we need parabolic scaling. If the diameter in space is the same order as the diameter in time to the power half, then these constants are reciprocals of each other, and then you can construct Scott-Zane operator, and then using bubbles, add bubbles, you can do the Fortin. That's basically like, that's the reason why we need the parabolic scaling. Okay, we have another problem. Inside our setup point problem with this inner product now involves these fractional norms. We cannot evaluate, so we have to cook up a preconditioner. And since we have complementary direct and inverse inequalities, you can do it with multigrid. If you are familiar with multigrid for, say, Poisson problem, if you're familiar with the multigrid theory, it works always with direct and inverse inequalities. And we have them here. Yeah, because we have this strange scaling, we have other norms, and with fractional norms, but because of this strange scaling, we apply everything that you know for elliptic problems can be transferred to this setting. So we use multigrid. So we replace this equation by multigrid preconditioning. That's what we do. Okay, that's skip. And here is an example. I take here a simple problem, an interval in time and a two-dimensional spatial domain. I do heat equation, zero forcing term. I take an initial condition equal to 1. That seems harmless, but this is actually a very difficult initial condition because at the lateral boundaries of the space-time cylinder, you enforce 0. Yeah, but the initial condition is 1. So the initial condition 1 meets the 0 condition at the lateral boundary, meaning that on the intersection of the bottom of the space-time cylinder, this is here, and the walls of the space-time cylinder, you have a discontinuity. So over this whole intersection, the solution is discontinuous. And that means that you need strong local refinements near this whole intersection in order to be able to approximate the solution. And that's what you see here. So the method does this. We take polynomials of degree 1 in time, and we tensorize this polynomial of degree 1 in space. And then using additivity, we get the best possible rate you can hope for. And if you increase the polynomial degree in space, then we see an improvement, but we don't get the rate as for smooth problems. So I expect that this is the optimal rate you can get, but it's not all. If the solution is very similar, then even with additivity, you don't get the rate as for smooth problems. Okay, but we have no proof of these statements that it is the best you can expect is 2 over 5. Okay, now method 3. Method 3 is simpler, and so I can speed up a little bit. So we have the heat equation again. Now you can make it more general. What we do, we write F, we split it into 2 parts, but when F is L2, the second part is 0. So what we do here, we make a first order system. So we introduce the gradient of u, think of f2 being 0, we introduce the gradient, the spatial gradient of u, or minus the spatial gradient of u, we introduce there's a new variable, w, and then the heat operator is just the, whoa, wrong button, sorry. Oh, no. Yeah, here. The partial derivative of u plus the spatial divergence of w, I denoted as the divergence of the pair, should be equal to f1. And so this is just a first order formulated parabolic problem. And with those spaces, with this space x, with a pair of uw in L2, in time, taking values in h10 times the w is just L2 in time, sorry, L2 in the time space cylinder. With this additional condition that the divergence is in L2, this operator G is boundedly invertible from this strange space X times multiple copies of L2. So that's very good. The original problem is equivalent to the first order problem, and we can just minimize the residual in L2. We can compute that. Yeah. Okay. And now let's have an example. If I take the spatial domain of dimension 1 and I take linears, then the best rate I would expect, if I have a smooth problem, the rate that you would get is a half. Now I take the following data. I take a forcing term equal to the constant 2, and I take an initial condition equal to 1. So again, this nasty singularity. Then what we observe are a rate 0.08 if you do uniform refinements, and if you do adaptivity, it improves, but you get 0.17, which is still far away from a half. And this has a reason. This is part of the graph norm, and the interpolation error in this term depends on the pth plus 1 order derivatives of u and w. And but because w is the gradient of u, the spatial gradient, it depends on the pth plus 2th order derivatives of u. And that's the problem with this method, that you couple u and its spatial gradient. And this would be solved if you would be able to apply finite elements that come with a commuting diagram, so that errors in this term only depends on higher order smoothness of this term. But we try to do that, and I go a bit quick. If instead of using simplices you use prismatic elements, then you come closer to a commuting diagram. So there are many details that I won't show you that. So it's initially you think, okay, I have a perfect method. My residual is in L2. I just do L2 minimization. I make a triangulation of my time space cylinder. Everything will work well. Now, if you take a simplicial partition, then you get disappointing rates. But if you use prisms with hanging nodes, which are more complicated to program, then you get better rates. Yeah, so you get here nearly optimal rate. I think I forgot one. If you have this mild singularity initial condition, you get optimal rates. If you make the singularity worse, you get slightly worse rates. This is in two-dimensional space, and there are also problems that even with this method, with the improved method, you don't get optimal rates. Okay, now you can apply it for optimal control. I skip that. This is something I want to present, if the chairman allows me 5 minutes, okay. So I want to show you how it works with the reduced basic method. And now I have a problem with parameters. These parameters are so-called parameter separable, so that the parameter A depends on the parameter, but it's a linear combination of fixed parameter independent AQs, and in front of them there are coefficients, and we assume the same form of the parameter dependence for the other parameter B, C, and also for F. And what we do for selected values of the parameters, we compute for sufficiently large trial space, we compute a virtually exact solution. This is known the truth solution in reduced basis methods terminology, or they are called snapshots. So for several parameters of mu, we compute the exact solution, so to speak. And then online, this is the online phase, given any parameter value, we compute the best approximation, or we minimize the residual over the span of the snapshots. That's what we do. That's the idea of the reduced basic methods. And then online, the costs depend polynomially on the number of snapshots that we use, but typically the number of snapshots is small, and the costs then are independent, or I do it again, sorry. The costs then are independent of the finite element mesh that we use for the offline computation. Now, how do we select the snapshots? Now, suppose I have 10 snapshots, then I select snapshot number 11 in such a way that it maximizes the error from the approximation of the first 10 snapshots. And that's what we do. So we always choose a new parameter from a training set, for which the approximation from the previous snapshots is as worse as possible. Okay, and now compared to the usual reduced basis method for parabolic methods, we get the complexity reduction in space and time. We don't need POD if you're familiar with this business. The theory is as solid as for elliptic problems, in particular the posterior error estimation. And in test is much faster online and also offline. Now I do a simple problem here. This is how the error in the training phase decays, and it decays exponentially. So we stopped when we have selected 21 snapshots. And now, given these snapshots for new parameter values, we approximate the solution as a linear combination of the snapshots by minimizing the residual. And this is what happens. So we have two sets of parameters. First, we took the parameters this form, and we vary mu1 between now 0 and 0.5. And in the blue, we have this set of parameters, and we vary mu2. And what you see is the dotted lines are the errors in the truth solutions, and the solid lines are the errors in the reduced basic methods approximations, and sometimes they are equal because apparently this value of the parameter was selected as a snapshot value, but otherwise you get, of course, higher errors, but not so much. They're close together, whereas we use only 21 snapshots. Okay, this is the conclusion, and I gave this presentation earlier, and then I said, but this is not the end because I have something more. But this time I think it will be the end because I spent enough time. So we have discussed these solution parabolic equations, and potential advantages are for non-smooth solutions, for parallel computing, and for applications that require the whole time evolution at the same time. So for reduced basis methods, for optimal control problems, for data assimilation problems. And we have discussed 3 different variation formulations. And currently I'm working on a generalization to quasi-linear parabolic PDEs. That's a nice topic because there seems hardly anything known about those equations, even continuity of the solution in terms of the data seems not to be known. I mean, the only thing that's known that there is a solution. That's good, but there's not enough for numerical approximation. Okay, and here's something more that I skipped. So, meshes. Thank you for your patience or attention.